Boyle's law and ideal gas behavior is the name of this video, and I'm welcoming you all this evening. Thank you for watching. I am Mr. Ish. You know what Boyle's law is? It describes the inverse relationship between pressure and volume. You can say it as this: PV is equal to K. You can also, from this specific expression, understand that P is equal to K over V, or you can say pressure is inversely proportional to volume. If the pressure goes up, the volume must come down. As the volume goes up, the pressure must come down. You can understand that very easily by means of a piston. There's a certain volume over here. If the piston is pushed down, of course the pressure in here is going up and the volume is coming down. But in that same system, if that piston is pushed up, now the pressure is going down and you are automatically increasing the volume because you're increasing the space which is available for the molecules to move. Always remember, pressure and volume are inversely related to each other. Given that in mind, how does Boyle's law relate to ideal gas behavior and non-ideal gas behavior? Think about an ideal gas. Ideal gas is that gas which exists under conditions of high temperature and low pressure. The key point over here is this: low pressure. This will signify by means of Boyle's law you will have high volume. As a result of this high volume and low pressure, what will be the outcome in terms of the ideal gas? You're going to have more intermolecular space. You know that because the volume has increased. There's more volume or more space between the molecules, more intermolecular space, which means what? Your molecules in that specific container or in that system will interact less. High temperature will signify what? You'll have molecules with more kinetic energy. There will be more Brownian movement, random Brownian movement. Molecules will be moving around more frequently, but since there's more volume, they will interact with other molecules less. Another assumption of ideal gas is this: that the volume of the particles or the volume of molecules, we can say that volume of the gas molecules is insignificant in relation to the volume of intermolecular space. And I'm going to abbreviate that as intermolecular space. How is this significant? If the volume of the molecules, the size of the particles, is insignificant in relation to the volume of space, it means again this specific fact: the molecules will interact less with each other, and when the molecules do interact, there will be no clumping of the molecules. You will have here what will be called elastic collisions. When one molecule hits another, you will have a complete transfer of kinetic energy from one molecule to the other, and that second molecule will continue in the same pattern or in the same behavior as the molecule it collided with. There is no loss of energy here with regards to generation of heat. This is ideal gas. Ideal gas conditions may not exist in the reality, but this is how one would make assumptions with regards to real gases. You start with an ideal situation, then you modify it with regards to what the reality is. Because of all of these particular factors, low pressure, high volume, high temperature, you will see elastic collisions. The kinetic energy of the system and of the molecules interacting stay the same after collision. You have to now contrast this with a non-ideal gas and non-ideal gas conditions, and you will see how things will be drastically different. Now, when you're talking about non-ideal gas, you're thinking about the reality or real gas behavior. In this particular situation, you're thinking and looking at a system which has low temperature but it has high pressure. But because it has high pressure, it's going to have low volume. And this right here is perhaps the most important part. You're going to have a gas which is being compressed, or a system that's compressed because of the high pressure, and there's low volume. But because of all of this, a certain number of things will happen. Volume of intermolecular space, which is small. As a result of this low volume, you will see that the volume of intermolecular space is small. That is, the gas particles which exist in that system, there's less space, less freedom of movement between those gas particles. But because of this low temperature, the molecules will have less kinetic energy. If you're decreasing the temperature, you're obviously going to have less kinetic energy. Each of the gas particles will move around less frequently. But the most important part is this: the volume of intermolecular space, which is small, and this leads to one important outcome, and that outcome is this: the volume of your gas particles is significant now. It's gonna be no longer insignificant, but it's significant in relation to volume of intermolecular space. As a result of the volume of gas particles being significant now with regards to the space between those particles, you will see a bunch of things as a result of that. You will see clumping. When one molecule interact with another, it will have a tendency to clump with that other molecule, and as a result you'll have inelastic collisions. A good way to understand what inelastic collisions is two billiard balls, one hitting the other, but they have Velcro patches on each other. As the billiard ball hits the other ball, because of the Velcro, it rather would stick. And if it doesn't stick, it may not continue on with the same velocity or in the same direction and all of that. You're going to have inelastic collisions, and because of this, the kinetic energy of that interaction will not be the same. You will have a loss of that kinetic energy as a result of heat generation. What is the reality is a balance between the non-ideal gas and the ideal gas. The main point you want to remember is for ideal gas, you're seeing high temperature, low pressure, but high volume. For non-ideal gas, you're seeing low temperature, high pressure, but low volume. The interactions over here are going to be significant because the gas particles are now rather significant in terms of their volume with regards to the space between those particles. Because the total volume is decreased, you're going to be seeing a lot of gas particles which will be clumping together as they interact, and the collisions are definitely inelastic versus elastic in the ideal gas conditions. Keep all of this in mind, and thank you for watching this video. Have a good day.